This video discusses sample problems for transmission line parameters. Sample problem number 1. Consider the 3-meter long lossless transmission line. It has a characteristic impedance of 120 pi ohms, terminated by a short circuit and excited with an electromagnetic wave that has a frequency of 37.5 MHz. The question is, what is the nature of the input impedance? First, let's list all of the given. We have our characteristic impedance, Z sub O, it's equal to 120 pi ohms. Next, we have our load impedance equal to 0 ohms. We know that this is 0 ohms because the problem states that the line is terminated by a short circuit. Then we have the frequency of our electromagnetic wave, it's equal to 37.5 MHz, or 37.5 times 10 raised to the 6 Hz. And then the physical length of the line, we have L equals 3 meters. To solve for the wavelength, it has the formula wavelength equals V sub P divided by F. V sub P is our velocity of propagation. It is equivalent to the speed of light, which is 3 times 10 raised to the 8, since there is no mention of the kind of medium of the transmission line. Our frequency is 37.5 times 10 raised to 6. So we solve for our lambda, our wavelength, we have 8 meters. The electrical length is given by beta L equals omega times L divided by the wavelength. Omega is 2 pi. The length of our line is 3 meters divided by our lambda, which is 8 meters. So we have 2 pi times 3 over 8. And then solving for that, we have 3 pi over 4. So now we have the electrical length and the impedances are given. We can now solve for the input impedance of the line. For a lossless transmission line, the input impedance is given by this formula. Z sub in equals Z sub O times the quantity of Z sub L plus J times Z sub O times the tangent of beta L, which is our electrical length, divided by Z sub O plus J Z sub L times tangent beta times L. So substituting all of our given to this equation, we have Z sub in equals 120 pi times the quantity of 0 plus J 120 pi times the tangent of 3 pi over 4 divided by 120 pi plus 0. So solving for this, we have Z sub in equals negative J 120 pi ohms. And since Z in, our input impedance, is negative, it suggests a capacitive behavior. Sample problem number 2. For a transmission line with incident voltage E sub I equal to 5 volts and reflected voltage E sub R equals to 3 volts, determine the reflection coefficient and SWR. Reflection coefficient has many formulas, but for this problem, we're going to use this formula, since our Vref and Vins is already given. So to solve for the reflection coefficient, we write the reflection coefficient is equal to our Vref, in this case is 3 volts, this is our reflected voltage, divided by our Vins, which is our incident voltage. In this case, it is 5 volts. So let's solve for that. 3 divided by 5, we have our reflection coefficient equal to 0.6. Notice that the reflection coefficient is a unitless quantity, since both voltage from the numerator and the denominator would cancel out. Next, we have to solve for SWR. To solve for SWR, we use the formula Vins plus Vref divided by Vins minus Vref. So let's plug in all the given to this formula. We have SWR equals 5 plus 3 divided by 5 minus 3. So solving for that, we have SWR equals 4. Again, SWR is a unitless quantity. Now, you have solved for the reflection coefficient and SWR. You may check if your answer is correct by looking at the values closely. The reflection coefficient should have an absolute value that is equal to or less than 1, while the SWR should have a value that is equal to or greater than 1. Sample problem number 3. Determine the SWR for a 75 ohm transmission line that is terminated in a load resistance R sub L equal to 50 ohms. Now to solve for this, we have to recall the formula for SWR if we are given both the characteristic impedance of the line and the load resistance is SWR equal to Z sub O divided by RL, or SWR is equal to R sub L divided by Z sub O. Now, this needs a little judgment on our part to decide which formula that we will use. In this case, we can see that the characteristic impedance Z sub O is greater than the load resistance R sub L. So we're going to use the first formula, SWR equals Z sub O divided by R sub L. So let's just plug our values in this formula. We have SWR equals 75 divided by 50. And solving for this, we have SWR equals 1.5. Again, take note that this is a unitless quantity since both the ohms unit in the numerator and in the denominator would cancel out. And we can see that this answer is correct because it is equal to or greater than 1. Sample problem number 4. A power meter inserted into a transmission line reads 1,150 watts of forward power and 50 watts of reflected power. The question is, what is the VSWR? So the formula for VSWR, given the forward power and reflected power, is this. VSWR equals 1 plus the square root of P sub R, this is our reflected power, divided by P sub F, this is our forward power. All of that divided by 1 minus the square root of P sub R divided by P sub F. So let's just plug our values in. We have VSWR equals 1 plus the square root of 50 divided by 1,150. All of that divided by 1 minus square root of 50 divided by 1,150. Solving for that, we have VSWR equals 1.53. So this is an easy problem. Next, for the last problem, we have sample problem number 5. A 40-meter long transmission line shown has a VS equal to 15, bar angle 0 degrees, VRMS. Z sub O equals 30 plus J 60 ohms, and V sub L equals 5, bar angle negative 48 degrees, VRMS. If the line is matched to the load, calculate the input impedance, Z sub N, the sending end current, I sub N, and the sending end voltage, V sub N. For a matched line, the input impedance Z sub N is also equal to the characteristic impedance of the line Z sub O, so Zn is equivalent to 30 plus J 60 ohms. Now for letter B, Let's first solve for the sending end voltage, V in. So the formula for this is V sub in equals V sub S times Z sub in divided by Z sub S plus Z sub in. For a matched line, our Z sub S is also equal to Z sub in. So we have V sub in equals 15 bar angle 0 degrees. This is the V sub S times 30 plus J60 divided by 2 times 30 plus J60. So solving for this, we have V in equals 7.5 bar angle 0 degrees VRMS. Let's not forget the unit. It's VRMS coming from V sub S equals 15 bar angle 0 degrees VRMS. Next, let's solve for I sub in. To solve for the sending end current, we just need to divide the sending end voltage divided by Z sub S and Z sub in. So we have I sub in equals V sub S divided by Z sub S plus Z sub in. Plugging in the values, we have I sub in equals 15 bar angle 0 degrees divided by 2 times 30 plus J60. And solving for this, we have I sub in equals 0.1118 bar angle negative 63.43 degrees ARMS.